Hello, geometry. Welcome to square roots and simplifying radicals. So this is one of those things that you may or may not have learned in Algebra 1, and it's something that we're going to use in geometry. So it's going to pop up as we go into trigonometry. So it's a great time, and Pythag, it's a great time for us to talk about this. So our objective here is to evaluate square roots and simplify expressions. We're going to just use the numbers. We're not going to deal with variables. But when we simplify square roots, that means if a radicand is not a perfect square, the answer is irrational, right? We usually round those answers. Well, I don't like it. I do not want rounded numbers. It's not precise. It's not exact. Exact answers only, nothing rounded. So if you get 3.14 blah, 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 whatever that might be, you're not going to write down 3.14. We're going to write down 2 square roots of 7 or something like that. So exact answers only. They're harder for us to wrap our brain around to understand as like, where does this lie on a number line? But they're more precise. So perhaps, for example, we might have 2 times the square root of 10. That's an exact answer. So if we end up with something, if we start out with something, we need to find a perfect square that is a factor of the radicand. So in other words, I might start off with something like a square root of 40. So I have to ask myself, are there any perfect squares that are factors of 40? Well, I know 8 times 5 are factors of 40, but 8 isn't a perfect square and 5 isn't. 10 times 4 multiply to give us 40, and 4 is a perfect square. So we have to know or be able to find that list of perfect squares. So your answer will be an integer, like 2, multiplied by a square root, say square root of 10. So somewhere on your paper, it would not hurt to write down a list of perfect squares. So when we try to figure out what are factors of, say, our example 40, we're only looking for numbers that are on the perfect square list. Probably out of the 2 factors, 4 times 10, one will be a perfect square, like the 4, and one will not be a perfect square. So let's talk about a square root of 48. Well, 48, if I tried to do that, it would be like 6.9 something, 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 something. Exact answers or exact numbers only, no rounding. So I have to ask myself, what perfect squares go into 48? So I think over on the side or in the margin, we need to jot down a list of perfect squares, right? So 1 squared. So 1 is our first perfect square. 2 squared, so 4 is a perfect square. 9 is a perfect square. 16 is a perfect square. 25. You getting the idea, right? 36. 49. We could keep going for like this for days. Let's go through, I don't know, 12 maybe. 64 is a perfect square. 81. We all know 100 is a perfect square. 121 is a perfect square. And 144. We could keep going. 13 squared is 169. 14 squared. We could keep going. 196. We could keep going through all those. So when I say look for a factor that is a perfect square, we're looking for one of these numbers. So when I use the example 40, 4 times 10 is 40, and 4 is on this perfect square list. So 48, I go down this list of perfect squares. 1 doesn't help anything. 4 does go into 48. Let's see if there's something larger. 9 does not go into 48. 16 isn't 16 times 3. So what I'm going to do is I'm just going to write this as the two factors, right? 16 times 3 is 48. And here's the cool thing. 16 is a perfect square. What is its square root? I always cross it out. So 4 with the square root of 3. So that square root of 3 can't be broken down. It's not a perfect square. You just bring it down. The 16 is a perfect square, so I write down. So square root of 5 times square root of 10. That's not helpful, right? Because neither a 5 or a 10 for problem number 2 are perfect squares. But if I multiply those out, that's 50, right? 5 times 10. We can multiply those. They're called radicands, the number under the radical. We can multiply those radicands and we can get a 50. Now I look at my list of perfect squares. Are there any perfect squares that are factors of 50? We know this. This is an easy one, right? 25 times 2. Write both of those factors down under its own radical. So it was broken up, we multiplied it, and then we broke it up differently. We're allowed to do that. So 25 is a perfect square. What's its square root? And what do you do with the square root of 2? Bring that guy right down. So you've got 5 times the square root of 2 for your final answer. Now, I do know that some of you have calculators that will do this for you. That's really fabulous. Congratulations. I need to see your work, what you're doing. You can't just go from square root of 48 and write down 4 square roots of 3, like you know that by heart. Also, probably on a assessment quiz or a test, I'll probably trade you out your fancy, I call it a cheater calculator, for a scientific calculator. Still just as good, but it doesn't break those radicals down. Some people get mad at me for that, but I want to know that you know how to do it, not your calculator. So let's talk about when we have square roots with a quotient. Notice this example, the square root of 81 over 25. Ugly, right? Well, here's the thing. We can break down the numerator and the denominator separately and then deal with the issue. So I could put an equal sign here, and I could say, well, that's like the square root of 81 over the square root of 25. I don't want to do too much work. I'm thinking about what we're going to talk about next. I don't want to do too much work right now. So I'm just going to start by saying, is either one of these numbers a perfect square? So forget it's a fraction, just look at the numerator. 81, is that a perfect square? Why, yes it is, right? 9 times 9 is 81. So 9 is its square root. How about 25? I'm done with that problem. So you're allowed to break a fraction down into 2 separate square roots, numerator over denominator. Sometimes that denominator is not always a nice, perfect square root of 25. Maybe it's a square root of 30. Then we need to go on to this next thing that is rationalizing the denominator. So first of all, please note that this is the denominator. Nobody likes a fraction, I know, but even worse than that is if you have a square root in the denominator. That's a problem. We don't care what the numerator is doing, the denominator is not allowed to have a radical. So when you write down a final answer, you can't have a radical or a square root in your denominator, against the rules. So we have to rationalize the denominator. So to do that, we multiply both the numerator and the denominator by whatever that square root is in the denominator. Multiply the numerator and denominator by the denominator. Please show your work on this, because some people try to take shortcuts and then it gets a bit messy when we can't figure out what's happening. So just like we did in that last problem with the easy fraction, we are going to do each part separately. So once you multiply the top and bottom by the denominator, you're going to just do numerator times numerator, denominator times denominator, break those down, simplify whatever you need to do separately. So always keep them as 2 separate pieces. So let's start with an easy one here. 3 over the square root of 5. Well, if that guy was flipped over, no problem, right? But that square root of 5 in the bottom of the fraction is what I am objecting to. I cannot have a denominator that has a radical. So I'm going to multiply the top and the bottom by the denominator. So in other words, I'm going to multiply by a square root of 5 over a square root of 5. It seems really weird, I know, but really anything over itself is 1, right? So we're not really changing this fraction, we're just changing what it looks like. It's like when you get a haircut, you're still you just have a different haircut. So when I do this, I'm going to multiply, but I'm going to do the top and bottom separately. So 3 times a square root of 5. We can't cross over that radical box, so what's on the outside stays on the outside. What's on the inside stays on the inside. So this is 3 times the square root of 5. Top is done. So now we look at the denominator. Square root of 5 times the square root of 5. Well, they're both underneath the square root box, just like that 5 times 10. We're going to do that. So that would be a square root of 5 times 5 is 25. Here's the beautiful part. It will happen every time. Do you notice that the square root of 25, 25 is a perfect square. What's its square root? 5, right? So I've got 3 square roots of 5 over 5. That is my final answer. The top is not pretty, but I don't care what I've got going on in the numerator as long as the denominator does not have a radical. If I could simplify, it's kind of like if it was 3x over 5, I could simplify. Let me give you a different example. If it was 6x over 9, right? We know that we could simplify this and make it 2x over 3. We do the same thing if it's a radical. 6 square roots of 2 over 9 will become 2 square roots of 2 over 3. It's still 2/3. We just have a square root of 2 instead of an x. So if you can simplify those outside numbers, feel free to do so. Last example, let's do this one. So the first thing when I've got a big radical around a fraction is I just split it up. So I'm going to call that a square root of 8 over a square root of 3 because it's just too messy to me. Again, I'm objecting to the square root of 3. I do not keep radicals in the denominator, so I'm going to multiply top and bottom by that denominator. I don't care about the top. I only care about the denominator. So do the top and bottom separately. I'm going to ignore this. So square root of 8 times square root of 3. Well, they're both underneath the square root, so 8 times 3 is 24. When I do the denominator, square root of 3 times square root of 3, they're both underneath the square root, so right, square root of 3 times 3 is 9. Forgot to put my fraction in there. So now, you probably already saw one thing we can simplify. There's actually 2 things we can simplify. I'm going to transfer this over, bring this down. Whoa, not like that. There we go. So I got a square root of 24 over a square root of 9. Well, you probably immediately are going to say, oh, square root of 9, that's 3, right? No coincidence, that has to happen. Square root of 24 is not a perfect square. It's probably 4.9 something. But are there any perfect squares that go into 24? Let's see, that's going to be, I know 2 times 12, but 2 is not a perfect square and 12 is not a perfect square. 6 times 4, that works, right? 3 times 8 doesn't work, but 6 times 4 works. Why does 6 times 4 work? Remember, one of these numbers has to be a perfect square. The 6 is not, but the square root of 4 is 2. Always write your number out in the front. So I've got a 2 with a square root of 6 on the top and that nice 3 on the bottom. Final answer. Don't look at these like one giant problem. Look at them bit by bit, and they get easier as you go. I want to make sure that everybody knows how to break down a radical and simplify, rationalize the denominator. That is it for section 09. So hopefully it was a review. If not, hopefully it feels easier to do. Have a great day.